All right, let's jump into our first reaction, and we're going to be looking at hydrohalogenation. So again, we're looking at electrophilic addition to alkenes. And so in a a hydrohalogenation, we are going to be adding a hydrogen to one side of the double bond and a halogen, we'll just use X there, to the other. And most commonly, those halogens will be chlorine, bromine, or iodine. It's very, very rare to use fluorine. So let's take a quick look at this. So we're going to take this alkene and we're going to react it with HX. I'll just kind of be generic right now, and then we'll get a little bit more specific. We'll do this at low temperatures just so that we can not have the reverse reaction occur. And a hydrogen will go to one side of the double bond and a halogen will go to the other side. Now, in this case, it does not matter which side the hydrogen goes to, which side the halogen goes to. I will talk in a little bit about what happens, what do we do when it does matter? And you get different products depending on where the hydrogen and the halogen goes. But before I get to that, let me lay a foundation of like what is actually happening here. So let's talk about the mechanism. So the first thing that happens in the mechanism is we're going to use the pi electrons as a nucleophile, and the hydrogen in our HX is going to be the electrophile. All right, so here is our first step. I'm going to jump up here. So we're going to use these hydrogens as, I'm sorry, the pi electrons, like a base in this case, and pull off a hydrogen. So the arrows there were showing making a bond to hydrogen. The bond between the H and the X, those electrons go back to the halogen. And so one of the carbons that used to be the double bond, I'm going to highlight those two carbons there, gets the hydrogen, and the other carbon becomes a carbocation. This is the rate determining step of the reaction because it requires going from a carbon that has a full octet to one that doesn't. Now, notice that one of the other products of this step is we have X minus. Well, I just kind of want you to look at it and say, what would be the natural thing to do here? You have something positive, you have something negative, you have a nucleophile, you have an electrophile. So let's make a bond between those two. And so hydrogen has gone to one side of the double bond, and the halogen has gone to the other side. Now, again, if I had switched this up, I would have gotten the same exact product. So what if I put the hydrogen over here and the X over there? It's exactly the same. So let's talk a little bit about a couple of implications of this mechanism. We're going to be looking at regiochemistry. So where does the hydrogen go? Where does the halogen go, especially when it matters? And then we're going to look at stereochemistry because we're forming a carbocation. And what happens if we make a new chiral center? All right, so let's deal with the regiochemistry first. In the previous example I did, it didn't matter where the hydrogen or the halogen went because we got the same product. But let's look at this case here. In this reaction, there are two possibilities. Either the hydrogen goes here and the halogen goes there, or the other way around. Now, let's see if we can figure this out with the knowledge that you have. What we're going to do is look at the first step of the mechanism. And what would the carbocation look like if the first possibility, our first product that we drew there, what if that were the product? What would the carbocation it came from look like? Well, if the hydrogen went here, the other carbon would get a positive charge. Now, what does that look like to you? Does that look nice and stable? No, that's really bad. That's a primary carbocation, does not exist. You can't even form it. So what's the other option? Well, the other option is the hydrogen goes here, and then we get this carbocation. What does that look like? That looks a whole lot better. That's a much more stable tertiary carbocation. And so that's where our nucleophile will attack, and why, if we were to do this reaction in the lab, we would only observe that one product, not the other, because the other product that I crossed out there comes from a carbocation that is so unstable it doesn't exist. And so this leads us to a rule. This is something known as Markovnikov's rule, which basically says the hydrogen goes to the less substituted carbon. The halogen goes to the more substituted carbon. Markovnikov's rule basically um, tells you that this is what is happening. So you should be able to look at any reaction, not worry about drawing the mechanism, and know that you have to follow Markovnikov's rule for a hydrohalogenation. But the mechanism explains the why. The why is explained by carbocation stability. So on your homework or on an exam, I would ask you, what's the major product? And you'd be expected to know that you should follow Markovnikov's rule when it comes to the addition of HX. Now, not all of the reactions we're going to talk about in this chapter can follow Markovnikov's rule, but there are a couple that you need to use this regiochemistry um, in order to get to the correct product. All right, and then finally, let's talk about stereochemistry. And I'm going to go back to my very first example. Okay, so this was the result that we got. And I want you to look, actually, let me just back up a little bit because I get this question a whole lot. Students ask, well, where's the hydrogen at? You're supposed to add an H and an X. I mean, the hydrogen's there. It's just remember that, in um, our rules for these line angle formulas, we don't have to show the hydrogens. So whether you put it there or you don't, so if you wanted to put it there, great. If you don't put it there, then you're going to get the same points. Like showing it or not showing it, if it's a hydrogen, is not a requirement. It's just assumed to be there. So just kind of put that at rest now. But do you notice anything special about this carbon? That carbon has four different groups around it. It's got an ethyl, an X, it's got a propyl group, and then it's got a hydrogen that we don't see. So what do we call a carbon that has four different groups? It's a chiral center. And any time you make a chiral center, you're going to result in a racemic mixture. And you should be asking yourself, why? Why does that happen? Well, it can all be explained through the intermediate. After the first step here, the rate determining step of this mechanism, hydrogen went to one carbon, and we get a carbocation as the intermediate. Now, the hybridization of that carbocation is sp2. We learned that a long time ago. Its shape is trigonal planar. And because it's planar, the nucleophile can either come in from above or it can come from below. And it does this in a purely statistical manner where half of the time it comes from above and half the time it comes from below. So what does that mean? That means half the time our product has that X going up and half the time it has the X going down. And that's why we end up with the racemic mixture. Again, I want to highlight that you only worry about this if you make a chiral center. Notice I didn't care about that in this example because this carbon right here is not chiral. So I don't care about stereochemistry. But one of the things you always have to do when you finish a problem like this in these chapters is ask yourself, did I make one or more new chiral centers? If the answer to that question is yes, you need to address the stereochemistry. Now, there's one final thing I want to highlight with these reactions. And actually, I'm going to put this in a different color to make it really pop out because it's one of the most important things that students forget. You need to watch out for rearrangements. Why is that? What you're doing with carbocations. Now, if I were to ask you, draw the product of this reaction, most of you would be like, oh, I'm just going to add the H in the Cl. I'll put the H here, and I'll put the chlorine here because that follows Markovnikov's rule. But this is the minor product. The major product puts the chlorine on a carbon that wasn't even involved in the double bond. So how do we explain this? By looking at the mechanism. Following Markovnikov's rule, the hydrogen goes to the less substituted carbon. The other carbon becomes a carbocation. Anytime you form a carbocation, you need to always ask yourself, is there the possibility of a rearrangement? Because I can do a hydride shift to get a more stable tertiary carbocation. And now the chloride will come in, and that's how we get to the major product. All right, so again, you have to remember that anytime you deal with carbocations, there is the possibility, not the certainty, but a possibility that it may rearrange if it can become more stable.